So he had mentioned earlier, I do teach a PhD time series course, but I typically teach PhD, master's, and undergraduate levels. And so what I've tried to do is, it's scary, it's been like 20 years now. So I've been doing these courses for something like 20 years and trying to get it to be accessible to all levels, mostly intuitively, right? So there's going to be math, don't get me wrong. There's going to be plenty of math that we do, but we're going to try to make it, you understand the intuition and understand the underlying, basic theory. And if we can do that, and we can understand the programming, then I think once you get to whatever you're working on your topic, it's okay to use click button sort of approaches, or it's okay to switch to something else. But what we're trying to do is really understand the basics. So I tell my students this all the time. A lot of you, outsourcing and, machine learning is going to take away some jobs. And so our job is going to need to be, we need to tell the computers what to do. We need to understand the underlying models, but we also need to understand the output and being able to talk to, say, a supervisor or a politician or a boss or whoever you're interacting with who probably knows less about this than you, right? And so we're trying to have this whole sort of understanding. And so that's sort of the basic idea here. So the plan is, you've probably seen the slides. The plan is to start with just make sure we have all the terminology, talking about just simple linear regression for a little bit, but through a maximum likelihood approach. So I don't know how many people know maximum likelihood. If you don't, that's okay. We'll figure it out. If you do, then it's a refresher. And all right. So what we're going to do is show simple linear regression, but via maximum likelihood. Then go through some tools, and then I'm going to show how to do maximum likelihood via R. And so a lot of times you don't get this. A lot of times you're just going to go straight into the clicking buttons or calling a procedure. We're going to do that basic idea first. Now, after we've done that, then we'll move on to time series, specifically univariate and multivariate time series. So we're going to talk about how to do more or less box Jenkins. So box Jenkins is a relatively old approach, but it's still very useful and still widely used. And then we're going to move to multivariate time series where we try to relate X to Y, right? And try to discuss a bit about causality through things like Granger causation, but then also talk about how we can, talk about treatment effects and things like this. So we're going to try to cover a variety of things. I have a lot more slides than I probably have time. So it depends on how quickly we go. If we don't make it to the end, then I will give you a bunch of information. All right, so I assume everybody can see the slides that I have up right now. So this course is time series analysis. I am Daniel Henderson. We have gone through Statistical Horizons, and I'm pretty sure today's the 25th. So here's what we got. So what is time series analysis? So in the simplest form, what happens is your boss or somebody gives you a data set, and we plot it. So whether we're doing cross-sectional methods or time series methods, I always tell students to look at the data, visually look at the data. What people like to do is they like to get a data set and immediately run a regression without looking at the data at all. You have to plot the data. Every question on every homework I give for my students, the first part A is plot the data. Right? Whether it be a histogram or a time series plot or something like this. So when we plot the data, we can tell a lot from it. What does this time series show us? Well, okay, we have right over here, we have this is our dependent variable, and it ranges somewhere from 0 to 50. And this is our time. So from period 0 to period 50. You can think of this as, yearly would be, say, the year 1900, 1901, 1902, all the way up to 1950, say. All right, so that could be what you have here. what do we notice? This thing is upward sloping. And so it looks like over time, it's going up roughly linearly. All right, what else do we see? We see that there seem to be peaks ever so many periods. So perhaps there's some sort of seasonality. All right. The variation in this, the variation seems to be somewhat constant. And so you can begin to, I don't know if I'm not quite a Bayesian, but you have some priors about what you think's happening here, right? And just as important as this is data that somebody's given you. Now, I can model this without knowing anything about the process, but if we know something about the data, so this is US GDP, or this is, the trees per square hectare, or something like this, right? If we know something about the science behind it, then that'll help us model too. All right, so we're back to take this particular time series. We have our Y variable, we plot it versus time. And this is the way, most data was plotted for quite a long time. It took a very long time before people discovered what scatter plots were. I mean, time series was typically how everybody plotted data. All right, so for most of time series, we have this particular plot and we look at it over time, and somebody wants to ask, what's going to happen next year? Right? And so what it boils down to is we move from this plot, to this plot. I want to figure out what that point is. And, we're all relatively intelligent. We could see the path and we can put a dot on a line, right? And so that little blue dot is a pretty good guess at what would happen. So a large chunk of this short course is figuring out how do we get that blue dot. Now, in this particular setting, I could have drawn that and got a reasonable result, right? But if we're talking about, buying and selling stocks or hedge funds, and we're talking about fractions of a second, we want to be pretty precise with this, right? Okay, so in order to get that particular point, there are certain tools that I'm going to give you. Some of those tools are going to be trying to extract things out of that, and so that we're just left with a part that's a little more manageable. So we're typically going to be trying to estimate univariate time series, and we're going to want to look at these things in a stationary setting. And what we're going to mean by stationary is we want the mean, the variance, and the covariances to be constant over time. If that's true, it makes the math relatively simple. When that's not true, then it makes it a little bit more difficult. Now, we'll be able to do both of these. We're going to sort of assume relatively early that we're only dealing with stationary data, and then we'll talk about, okay, how do I deal with the data when it's non-stationary? The typical approach in the literature is just force it to be stationary, but that's not always my prior, right? So we'll talk about that too. All right, like I said, anytime you have a question, just bug me. Okay, so I think we sort of talked about a lot of this, but what do we want to do in time series analysis is, and this part is really, we want to develop a sophisticatedly simple model. There's this sort of trend right now to over math something, or to use machine learning, or to just throw high-powered equations at something. And so if you go to Wall Street, there are often people known as quants, and what they often take a lot of physicists and they throw a lot of math at a problem without understanding, say, the underlying economics or the underlying science. And so we want to develop a model which is sophisticated enough to handle the process, but at the same time be relatively simple so that we can interpret and predict. It's really easy to predict well in sample. You fit a high enough ordered polynomial to a problem, you can fit almost anything. But at that point, you're modeling noise, right? Our goal is not to model noise. Our goal is to model the underlying process in hopes to be able to forecast, right? We're also interested in interpreting the data. So maybe a social science would want to know if you increase X by 1, what happens to Y, right? So if you change the tax rate, what happens to, investment or something like this? Or if you institute some sort of treatment into a series, what happens over time, right? So, and then we're going to want to, test hypotheses. So whether or not a particular predictor helps and things like this. All right. So that's the basic idea, and this is what we're trying to do. Now, when we have a time series like the one that we plotted before, so a time series has typically 4 different components. The first one's known as a trend. So the trend, as we saw, typically can be modeled visually. So you can look at it and you can say, you know what, that first trend looked linear, right? Or maybe the trend looks quadratic, or maybe it's exponential. I took classes with a lot of entomology students when I was an undergrad, and they were modeling, reproduction of insects. And I think it followed exponential trends, which, makes me want to wash my dishes. So that can often be modeled visually. And that is something, if it's a deterministic trend, we can model as opposed to trying to get rid of. Then there's seasonal portions. So the first sort of introduction I had to this was I worked at a barbecue restaurant when I was in high school. And the woman who was the boss, she had 3 different books. And so in the first book, we would have to write down how many appetizers were sold, how many plates of ribs were sold, how many drinks, and so on. And then the other 2 books were the previous 2 years. And we would look at the same weekend 52 weeks prior, right? And say, on this weekend, it was the jazz festival, and we sold a lot of ribs or whatever. Therefore, we need to prep for this. We need to have more of these things. And so that sort of information can be modeled with knowing something about the data. We know at that festival, you're going to get a lot more of this type of food. So those are 2 things that we can, sort of use common knowledge. And all of us have that sort of, even people who work at a barbecue restaurant with no prior knowledge of statistics had some idea about, right? So we can see trends, we can see seasonal portion. The part that I'm really going to be teaching you is the irregular portion of this, which we have to try to extract using tools, right? And that's where, we're going to be able to gain some. I saw those spikes on that previous figure. I can put a dot there. I mean, that's not all that impressive. So what we're going to try to do is we're going to try to extract the trend, extract the seasonal portion, or model the trend, model the seasonal portion, and then use the tools that we have here to pick up that irregular part. And there's going to be some part that's left over, which we call the random component, right? This is what is often referred to as, we hope, is known as white noise, meaning zero mean, constant variance, and no autocovariance. This is something that we can't predict. These are shocks, but they're well behaved. And so we just realize that's the mistake we're going to make, right? We know that we're trying to make good predictions, but we know we're going to be wrong, right? But we hope that on average we're correct. That's sort of the basic idea. All right, so let's think about these 4 different components of a time series and see if we can break these down one by one. Okay, so this is the time series that we had before. The first part is a trend. So if you ask me, it looks like there is a linear trend that goes right through here, right? To me, it seems there's a linear trend. Now, we can either model that trend or we can try to remove that trend. Removing the trend, we'll see, is relatively simple. If I run a linear regression of y on an intercept in time, that will model that trend. I can take the residual, and that will be what we call the detrended series. And that detrended series would look something like this. So it looks like I might not have taken out the intercept because I see a non-zero mean. But now it looks like we have a mean which is relatively constant, right? So you have a mean that's relatively constant. Okay, so that's I took out the trend. Now notice that every peak, 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 you see that they're all at the same frequency. So there's a peak and I know what this is because I just generated data. There's a peak every 4 periods, right? So you can see these regular peaks. They're happening every 4th period. So if you can think about sales in the 4th quarter in the US is when all the retail firms make all their money in the 4th quarter, right? And so we're realizing that if we're having to hire employees, then we need to hire more employees for that quarter, right? So maybe we have what we know are seasonal employees. And so there's a seasonal component here. I can model that component, which is my preference, or I can remove that component. If I remove that component, then we see that we no longer see that exact frequency. So this is me modeling the seasonal component. All right, so I model the seasonal component, but you still see patterns here, right? So I still see a pattern. So then I use what I said, this is the irregular component. We use the tools of the trade, and we can remove this particular component, right? So if I remove this particular component, what I hope to be left with is noise, right? And so this is sort of the goal. We're going to make assumptions that our models are white noise, that the errors in our models are white noise. And so we're going to have the part that we can model and the part that we cannot model, right? And when we develop a model, then we estimate the model, we get the residuals. Our residuals should look like they're white noise. The residuals should look like they're just random. If they are random, then we did the best thing we could. We did the best we could. We make our forecast. We can live with that. If these are irregular, if these have some pattern, if these have some trend, then we've left money on the table, right? And we need to go back and we need to say, okay, there's something there. I need to go back and start over because there's something that's left over, right? So you want to be left with noise at the end of the day, stuff that you cannot predict, but is predictable in some sense, meaning that we expect it to be zero. We expect it to have a constant variance. We don't expect any pattern in this. And if that turns out to be the case, then we've done the best we can, right? And we're going to make mistakes, but those mistakes are not necessarily going to be big, and we expect those mistakes to be small, or we expect them to be zero. So that's sort of the goal here. All right. Any questions on the basic motivation at all here? Okay. So like I said, we're going to start off with univariate time series data. That's going to be the majority of the course. We're going to go through what's known as a Box-Jenkins framework. So there's a flow chart. And the flow chart will say, okay, let's check this, then let's do this, then let's do this, then let's check this. Okay, if the check doesn't work out, then we go back and start over. Get back to that point, and if the checks do pass eventually, then we can move on to forecasting. That's sort of the basic idea. I'll show you a table and sort of talk about it a little bit more. Our goal here is to construct point, interval, and density forecasts in this framework. That little blue dot that I showed at the beginning was the example of a point forecast. So it turns out in a court of law, only point forecasts are allowed, right? Only point estimates are allowed. You could say, what were the damages to this particular firm? Well, they lost $3,784.72. Like, you have to do it to the penny. Sorry, there's about a third of you are not from North America, so they're different currencies. But so you have, at least in the US, you have to get, in a court of law, it has to be to the exact penny. You can't say, well, it's between here and here. That doesn't fly, right? You have to give an exact dollar amount. And so we will give point forecasts. Now, maybe your boss wants that, or maybe your boss wants some sort of range. And so similar to confidence intervals in statistics, you can have forecast intervals. So you can say, okay, look, it goes from this level to this level. So you can have a 95% or a 99% forecast interval, which will say, I'm expecting it to be from this range to this range. That turns out to be pretty useful. You want to know, what are you going to make on average? Now, what's lesser done is something known as a density forecast. And so a density forecast will not only tell you what you expect it to be, it will give you probabilities. And so what's the probability that it's closer to the point forecasted relatively high if we assume normal distribution. And then if the tails are small, it means the probability of a big loss or a big gain is relatively small. Now, one of the problems with the 2008 financial crisis is they were assuming that those tails were really thin. And they were making normality assumptions when the probability of a loss was much harder. And so they were telling everybody they were relatively safe when they weren't. The other problem they made is they assumed no correlation between like foreclosures, which meant if your neighbor's house foreclosed, that makes the chance your house is going to foreclose a lot higher, right? And they were assuming no correlation. So we're going to be making assumptions and we're going to be using them, but we have to be very careful that these assumptions are true, right? And so for your particular data set, in your particular field, this may or may not hold. So we have to question all these assumptions. And so that's what I really like to emphasize is, look, I'm going to make an assumption here. What is the implication of a violation of said assumption, right? And if there is a violation, how do you fix that, right? So a lot of times we learn statistics and we say, well, in this world where everything works perfectly, then this is how it works. Like in economics, we talk about if all these assumptions hold, then the invisible hand comes through and it fixes everything, right? And assumptions often fail. And so we have to figure out when those fail, what are we assuming? Because a failure of that assumption could lead to catastrophic results, right? I mean, we saw what happened in the financial crisis and all the hardships that happened from making these statistical mistakes. Okay, so we'll also talk about seasonal data. This is very important. A lot of people's data is seasonal. And so what matters a lot is what happened 4 quarters ago and not necessarily the last quarter, what happened 12 months ago and not necessarily last month. We'll talk about multivariate models, which a lot of people will be interested in different fields. Me, myself, I'm more interested in multivariate models. We may be interested in marginal impact. So 1 unit change in X brings about a what change in Y. We may be interested in causality. I have X's and Y's, and I don't know if Y causes X or X causes Y, right? So we're often interested in prediction. So in economics, we're interested in housing starts quite often. How many new permissions to build houses? Well, the more houses are being built, the more people are working, the more people are spending. This ends up leading to like increases in gross domestic product. And so now we know that now, but not everything is clear which direction causality works. All right. Finally, we're going to talk about how to model and forecast with non-stationary data. There's 2 different types of non-stationary data we'll talk about. One is known as trend stationary, and that's when we had, say, that linear trend. And the other type is integrated processes, and this is unit roots. If you heard of random walks and unit roots and things like this, which are common in a variety of fields, we'll talk about how to address those 2, right? My particular preference is if it's trend stationary, we try to model it. And if it's integrated, then we often have to take differences. And we can talk about in these different scenarios, how do we interpret the data, right? How do we interpret the results? So that's really the main focus here. All right, so unless there's any questions, what we're going to do is this first part of the course. So we're going to do a review of linear regression. Specifically, I'm going to focus on maximum likelihood because it may not be familiar to everybody. Then we're going to talk about some tools which are really useful for time series analysis. Then, depending on how far we're in there, we either take a break or we're going to do some basic R programming. So that's sort of the plan for this first part, and then we'll move on to the next part. Okay, so let's talk about notation. Let's talk about parameters and other things like this. So we're going to consider a simple linear regression model. So I imagine most of you have had linear regression. If we have a linear regression, we had yi. So this is firm I, is some linear function of X. So this is the output for firm I, which is a linear function of the input for firm I, and we have this random error here. And you'd have, say, n different firms. All right, so you would randomly sample 100 different firms, and you would ask each of those firms, for example, how much output did you produce? How many inputs did you have? Something like this. And we'd be interested in estimating the parameters alpha and beta, alpha being the intercept, beta being the slope parameter, and the U was a random error term. And we made a bunch of assumptions about these, that the errors were mean zero, that they were uncorrelated with the X's, that the model was truly linear in parameters. And then we made assumptions about, say, homoscedasticity or no irrelevant regressors and things like that. So we're talking about in a cross-sectional setting, we're like this. Now, in the time series setting, we talk about one firm or one individual. I used to have it took stat from one professor when I was undergrad, and he always dealt with blood samples. And so you could take a particular individual, and once a week you can take their blood and analyze it, right? And so in this case, the time series is we're talking about one individual, one firm, one country, something like this. And we're going to measure that country over time. Now, in this particular setting, we're not drawing anybody at random. We have a particular firm, we have a particular person, and how my blood work looks today is a whole lot related to how it looked last week. It's probably very closely related to how it looks next week. My blood type's not going to change, right? And, my, good cholesterol, my bad cholesterol are going to have some sort of pattern, right? And so we want to see what's going to happen over time to, say, my LDLs, right? And then we can think about, well, how is my, how is my bad cholesterol related to my intake of fatty foods or something like this, right? So they ask me each week, how many times did I go to eat fried chicken, right? And I say, okay, I went twice, right? That's going to be related to my blood work here. But that's always probably related to my blood work in the previous period. So what we're doing right now is I want to tie this closer to what we learned in linear regression. So we're just going to say my blood work today only depends upon how much fried chicken I ate this particular week, right? And we can say that my guess is if this is a linear function, then this coefficient beta is probably positive when we're talking about my bad cholesterol, right? So my bad cholesterol is going to get worse as I eat more fried chicken. Okay, so Y is known as our dependent variable. It's going to be measured at time t. And X is potentially a set, or in my example, it's a single variable, but it's potentially a set of variables. And these are what we typically refer to as our independent variables. Alpha and beta are going to be our intercept and slope parameters. Those are the two objects we're going to try to estimate. And the UT is the idiosyncratic error term, which we're going to assume is going to be uncorrelated with X. That assumption is violated quite often, right? We're ignoring that for the moment. All right, so we have T different observations. So they're going to look at my blood work for 52 weeks. I go and get my blood taken. And for 52 weeks, I told them how many pieces of fried chicken I had that week, right? And then we're going to try to use that information to try to make estimates of alpha and beta, right? Because they want to see that if I eat an extra piece of fried chicken, how many extra points does that increase my LDLs? Okay, so ordinary least squares is what most of us learned. And what does ordinary least squares do? It is the parameter estimates of alpha and beta are obtained by minimizing the residual sum of squares. So the residual sum of squares, or exactly what it says, is the sum of the squared residuals, right? So the sum of the squared residuals. So we want to minimize that with respect to the parameters of the model. So when we want to minimize something, then it's a derivative, right? So if we remember from basic calculus, if you want to minimize a function or maximize a function, you take the first order conditions, you set them equal to 0. And that's where you find change points in the functions, right? And when it goes from positive to negative or negative to positive, that slope is going to be 0. And you're either going to reach a local max or a local min. Our goal in ordinary least squares is to minimize the residual sum of squares. So we want to take that derivative, set it equal to 0, make sure that it's a minimum. I know it is here, but so I take this first order conditions with respect to alpha hat and beta hat. So you're going to take the change with respect to alpha hat, or you're going to take the partial change with respect to beta hat, right? And what that derivative first order condition does is says, look, holding everything else constant, suppose I just changed the intercept. How would the residual sum of squares change? The second partial derivative says, well, suppose I kept the intercept fixed and I just changed the slope a little bit. How would the residual sum of squares change? Now, doing those simultaneously results in two equations with two unknowns, and we get our standard intercept estimator. So an intercept estimator is the sample average of y plus the slope estimator times the standard, the sample average of x. The sample average, the slope estimator is the summation t from 1 to cap t of yt minus y bar, xt minus x bar. And if you divided the numerator and the denominator by t minus 1, which is just multiplying by 1, the numerator is the covariance, and the denominator is the sample variance of x, right? And so this is things that we learned, of course, in intro regression. All right, so that's the stuff supposedly we know. Now, we also hopefully learned the Gauss-Markov assumptions, and under these 6 assumptions, that we know that these estimators are unbiased, they're consistent, and they're efficient, meaning there's no way to do better under these particular assumptions. Now, the reasons why we have more statistics courses than intro regression is because these often don't hold, right? All right, so now, the important part here, which they don't always teach you, is the reason that they're efficient is because the OLS estimators under these 6 assumptions, and specifically the normality assumption of the errors, occur because OLS estimates are equivalent to maximum likelihood. And maximum likelihood is the efficient estimator because it not only assumes the functional form, but it assumes the distribution of the errors, right? And so what we're going to do now is we're going to talk about maximum likelihood estimation a little bit superficially, but our goal here is to construct what are known as log likelihood functions. So when you see the output from your regression, there's all that stuff in the bottom, like R square, adjusted R square, standard error of the regression, and there's always the one that says log likelihood. We're going to derive that, which is a useful measure, and we're going to talk about how we derive it, how it came to be, and then how do we get that particular number, right? Because I like to make my students know exactly how every number of that output is obtained, right? So when you get it and you see it, you can look and say, okay, that doesn't look right because of whatever, right? Because I have knowledge of how this works. All right, so we're going to consider a probability density function. So in your mind, just think a normal distribution, right? So think of f of y as a normal distribution. So a typical bell-shaped curve. Now, we use capital letters to represent random variables and little letters to represent particular values. All right, so you think about a normal distribution, right? So for some random variable y, so let's suppose my LDLs are going to come from some distribution. There are things that are hereditary, there are things that are out of your control. If you just took a random draw from a normal distribution, my LDLs will be somewhere probably around the average, right? Without any sort of intervention. Now, these are going to be conditioned on a set of parameters theta. So what we know about a normal distribution is it's fully characterized by the mean and the variance. If you know the mean and the variance, you know everything you need to know about a normal distribution, because we know there's no skewness, the kurtosis, there's no fat tails. And so we're going to know everything about that particular distribution. So if you can think about a normal distribution, this is what you can keep in your head. It's going to have mean mu, and it's going to have variance sigma square. Right? So think about that's the width of this particular distribution. So have this in your head when we're thinking about this, because this is what we're going to assume anyways. All right. Now, if we have T, if we're looking at the joint density, so suppose we have T independent and identically distributed observations. So in this case, suppose my LDLs only every week it's a new draw, right? Every week it's a new draw. It's like today, these are going to be your LDLs, right? There's no sort of continuum here. So we pull out T of these, and we may be interested in the joint density. So remember when we took intro stat, the joint density of f of x comma y, we would say, if they're independent, then the joint density is equal to the product of the marginals. So f of x comma y is equal to f of x times f of y if they're independent. So we're getting T different draws independently from say a normal distribution. This is the joint density, which depends upon theta. Because if you change the mean or the variance, then that bag of marbles or whatever you talked about in intro stat is going to look differently, right? All right. So if they're independent, you can write the joint distribution as the product of each of the marginal distributions, f of y1 times f of y2 times f of y3, all the way to f of yt, cap t. Okay. So that is known as a likelihood function. Right? So that's what a likelihood function is. What we're going to do is we're going to make some assumption about the distribution of those errors, those UTs. We're going to make assumption about that. And we're going to use that to try to extract the alpha and beta. All right. So this joint density is known as a likelihood function. Yeah. Now, I talked about earlier about log likelihoods. It turns out that it's often much easier to work with a log likelihood function. So it's not that you can't use a likelihood function. It's just as much easier, especially in what we're going to do, to work with a log likelihood. It's a monotonic transformation, so there's not a problem here. And so we're often going to work with the log likelihood. Now, what's nice about that, if we remember the products of logs, the log of A times B is the log of A plus the log of B, right? Where we had in the previous page, we had this product. So f of 1 times f of 2 times f of 3. That's hard to take derivatives, right? But if we have a sum, then it's the log of f1 plus the log of f2 plus the log of f3, and derivatives are a lot easier, right? Now, maximum likelihood estimation gets its name because you're trying to maximize the log likelihood function. So in OLS, we tried to minimize the residual sum of squares. In MLE, we're trying to maximize the log likelihood function. So very similar ideas. And when you look at the log likelihood function later on, you're going to see that we're going to get a minus residual sum of squares in there. And so you can see how minimizing one is equivalent to maximizing the other. And so this is how this is going to work. So we're going to want to maximize the log likelihood function with respect to theta. In our examples, we can think about the intercept and the slope. But we're also going to have to get the variance of the errors here because we made this distributional assumption. All right. In many situations, and that is not how you spell situations, in many situations, including this particular course, we're going to assume that this distribution of f is going to be Gaussian or normally distributed. All right. I wouldn't expect you to memorize this particular form, but I have because I've written it so many times. If we have a normal distribution, I had said the parameters that fully characterize this distribution are mu and sigma squared, the mean and the variance, right? Because we know it's symmetrically distributed about mu. Now, if your standard bell-shaped curve, this is the exact formula which gives that particular curve. So 1 over root sigma squared 2 pi, e to the minus 1 over 2 sigma squared y minus mu squared, right? And so we are going to end up making this assumption that u conditional upon x is IID. This assumption is okay. We're not saying something about the y's over time. We're saying that the errors conditional upon the x's are IID. We're not going to let these errors be related over time, right? We're going to assume the normally distributed mean mu variance sigma squared. So I don't need to estimate this, but I am going to have to estimate this. So my errors are going to be normally distributed. Mean zero variance sigma squared. We don't want the errors to be non-mean zero because that means that you're off target, right? You're pushed up or pushed down a little bit. And if you know you're off a little bit above or below, then you should adjust your shot, right? And so the mean zero is pretty standard. We're going to have a constant variance. Is normality the right assumption? Well, I just gave some example earlier where it may not be, right? The math is much easier with normal, but we have computers who can do a lot of this stuff. So I'm going to show you the math, and then we can talk about where we could tweak it if we needed to. If you want to make sure if you are somebody who's a financial advisor, you don't want their clients to lose their shirts, right? It's okay if they make more money than they expected. It's a real big deal if they lose a lot more than they expected, right? Or if you're talking about trying to preserve, as somebody in here did work with wildlife, if you're worried of what's the chance that all the babies die in some endangered species, and that probability is relatively high, maybe you have to intervene, right? And so we have to be very careful about these tails on these distributions and the shape of these distributions, right? That being said, we're doing all normal in this class. Okay, so let's go back to our simple linear model. So this is the model that we had before. We're assuming that y is a linear function of x, and we have these errors. And we're assuming that these errors, conditional upon x, come from a normal distribution. All right, so the way that we're going to write this is that conditional upon the x's, all the variation in y comes from the error. Let me say that again. Conditional upon x, all the variation of y comes through the error term. And so we can rewrite the conditional density as this. So we're going to look at the density of y conditional on x and the parameters of our model, alpha, beta, and sigma square. So what we're doing is sigma square is here. The mean of my particular density is this. It's y minus alpha minus beta xt. This is what? This is ut, right? So ut is equal to yt minus alpha minus beta xt. So I really just put in the mean of u, the expected value of ut, conditional upon xt is equal to 0, right? We made that assumption here. So we said the u conditional upon x is mean 0. So its expected value is 0. So the expected value of u given x is equal to 0. So what we have here is ut minus 0. That's the mean of this thing, right? So we have ut minus 0. That's what ut is. So y minus mu squared, right? So this is our variance term. And so what we have here is we have this density. Now, we assume the independence of these errors. And so we're next going to want to look at the joint distribution from f of y1 to f of y cap t, right? So if we look at so before we would have had the likelihood of alpha, beta, and sigma square was going to equal to the product t equal 1 to cap t of f of yt, conditional on xt and theta, right? All right. Now, if we take the logs, we can write this as the sum of the individual densities. All right. Now, if you look at the previous page, what do we have? So we have our likelihood function. This is 1 over 2 sigma squared. So what is this really? This is equal to sigma squared to the minus 1/2 power, 2 pi to the minus 1/2 power, right? And when we take a log of something, the power comes up front. So this first term here is minus 1/2 log sigma squared, minus 1/2 log 2 pi, and then log of e, they just cancel each other out, and we get minus 1/2 sigma squared, yt minus alpha minus beta xt squared, right? So that's the log of this normal. Now we can run this summation through. So the summation of a constant is t times the constant. So we get minus t/2 log sigma squared. This is also a constant, minus t/2 log 2 pi. This is really a nuisance term. When you take derivatives, this doesn't change, but we keep it around. And then we get the constant can be pulled out of the summation, and we get minus 1/2 sigma squared. Summation of, look at this. If we put hats in here, this is going to be the residual sum of squares. We have the minus here. We have essentially the residual sum of squares. This is non-negative because it's a variance. So this is going to, maximizing the log likelihood is related to minimizing the residual sum of squares. And this is why these two are related here. Okay. Now, almost all the measures you use, even R-square, adjusted R-square, log likelihood, Akayahi, Hanna-Quinn, Schwartz criterion, Bayesian information, all these different things you see at the bottom are all based on residual sum of squares in some sense. And so we can see that maximum likelihood is going to maximize the log likelihood function, but that's related to minus minimizing the residual sum of squares. Okay. So we want to maximize the log likelihood function. So what does that mean? Okay, we take derivatives again. So we want to take 3 first-order conditions with respect to alpha hat, beta hat, and sigma squared, because those are our 3 parameters. We set those each equal to 0, 3 equations, 3 unknowns we can solve for each of these. Okay. Luckily, here we have closed form solutions. In a lot of what we do, there are no closed form solutions, and the computer has to do it. So I'm showing you how to set up the most basic one. We solve for it, but later on, we're going to let the computer do all the work and show that they're equivalent. That's going to be the first R exercise. We set up the log likelihood function, and from there, you can manipulate it however you want, right? And we'll talk about how you manipulate it, but we'll show that it's equivalent in the setting where we know they're exactly equal. In practice, a lot of times we don't have closed form solutions. We got to hope the computer is doing its job, and we can, try to check for this, of course. Okay, so we got to take 3 first-order conditions. We got to take the change in the log likelihood function with respect to change in alpha hat. So let's just change. I don't have hats here. Please put in hats here. So you have to just change the intercept, holding all else constant, then change the slope, holding all else constant. Sorry, change the slope, holding all else constant, and then change the variance. This partial derivative is a little bit trickier. The way that I like to tell people is we're taking a derivative with respect to sigma hat square, not sigma. If you try to do it with respect to sigma, it gets a lot more complicated. Just think of this as a different name. Just call it, I don't know, psi, whatever you want to call it. If this is defined as sigma squared, this is a lot easier. People struggle with the sigma hat square. All right, so we have 3 equations, 3 unknowns. So you set each of these equal to 0. Well, if I multiply each side by sigma hat square, you're just left with this part here, right? And that is the method of moments expected value of u equal to 0 for OLS for the intercept. That'll lead you to alpha hat is equal to y bar minus beta hat x bar, right? So that's exactly OLS here. This is almost the same exact thing when we multiply each side by sigma hat square. That's the second normal equation for the expected value of u times x equal to 0, right, through method of moments or OLS. So we can see how we're going to get the exact same alpha hat and beta hat. This here requires a little bit more work, but we'll get a standard estimate. So like I said, setting each of these equations equal to 0, you get sigma hat, so alpha hat, which is the same as OLS. You'll get beta hat, which is the same exact version of OLS. And then you're going to get sigma hat squared, which is 1 by t, summation yt minus alpha hat minus beta hat xt, which is just simply the residual sum of squares. Now, the one issue here is this is 1 by t, and most of us know we need s squared, right? Where we have to adjust for the degrees of freedom, in which case there are 2 here. Now, this is a consistent estimator, but it's biased in finite samples, right? So MLE has that particular estimator, and it's not perfect, but it's consistent, right? So in practice, you're going to want to adjust for degrees of freedom. So that's not a big deal, but we know how to do that, right? Okay, so that's these. So what's nice here is that MLE is exactly equal to OLS, right? So what you are going to want to do is, this equation here is very useful. So with my undergrads, I make them memorize this particular equation. And then all we have to do is replace this. All the models we use in this class are just going to have different conditional expectations, right? So if we have if we just have an AR1 model, C plus phi yt minus 1 plus epsilon t. And if you don't know that, don't worry about it. We're going to get to there. We're just going to have yt minus c minus phi yt minus 1. And I plug that in here. And that's the whole difference. And in most of time series estimation, it's simply replacing that little part. So we saw how to get there. But now that we've gotten there, all we got to do is replace that little part, and we do all the same math. Now, in these other scenarios, it gets a little tricky when we have to take derivatives. Maybe there's not closed form solutions. Maybe it's too many equations to solve, but we at least know how it works, and we at least know what it's tending to, right? And so that part is going to be there. And I really like the idea of going through this in some detail in the code. All right, so we have our 3 different estimators. 2 of them are equal to OLS. The third one, we recognize where it comes from, right? All right, now, I talked about this before. So when you have your computer output and you run even a linear regression, even an OLS regression, they still report the log likelihood, right? Down at the bottom of the table, R squared, adjusted R squared, standard error of the regression, log likelihood. This is a log likelihood. So what is the log likelihood? Well, we're maximizing the log likelihood, just like we minimize the residual sum of squares. So in that output, it often has the residual sum of squares or sum squared residuals or whatever they call them, right? And that value is obtained by plugging the parameter estimates into the residual sum of squares. The residual sum of squares is this term. That number there is a scalar value, it's one particular number that's reported. And it's obtained by plugging in alpha hat and plugging in beta hat and taking, for each t, calculating that number, squaring it, adding it up. Likewise, for the log likelihood function, we plug in for alpha hat, we plug in for beta hat, we plug in for sigma hat square, and we look at each t, and we can calculate this value, right? And so that's something you can do, although it turns out it's a lot easier to calculate. It can solely be based off of this particular term, so it can make your life easier. So let's think about how that occurs. So we already recognize that that's the residual sum of squares, right? So that's summation ut hat. We also saw before that sigma hat square is equal to 1 by t, summation t equal 1 to cap t, ut hat square. That's going to tell you what? That T sigma hat square is equal to summation, or is equal to the residual sum of squares. Right? So I can replace this with T sigma hat square. And then you get some things to cancel out. And so you can actually just calculate the log likelihood solely with the sigma hat square, which pops out of that. When you have the estimator, it pops out. So you can calculate this by hand really easy. So every now and then, one of my students will say, oh, I'm having a hard time, extracting this from the program. Well, just calculate it yourself, right? I mean, a lot of these things, you've been taught how to do it. You know how to do it. Instead of spending 30 minutes trying to figure out what R is extracting, just calculate it, right? Sometimes it makes life easier this way. I tend to like to do just, let me get the result. Let's get it and let's move on. And so people talk to me about this all the time. I always sort of worry about using packages because sometimes it doesn't do something I want. And then how do I get it? So almost always code by hand. But for this particular class, if we didn't do that, we'd just be drowning in code. And so I'm going to show you some of this stuff by hand, and then we're going to move to one particular package because it gets really messy here. All right, so that's how you calculate a log likelihood. All right, so that's maximum likelihood estimation. Does anybody have any questions whatsoever on MLE? Okay. So that's MLE. Some of you may know it, some of you may not, but hopefully it's a good reminder either way. All right. Now, what I'm going to talk about now are a lot of tools we're going to need for time series. And so what we're going to do is we are going to talk about difference equations. And so we're going to do a lot with difference equations. And then it's going to feel repetitive because we're going to do it again. But we're going to do it again in our sort of time series setting. So it'll look a little bit repetitive at points, but it seems over time this is the way that it works. Now, of course, if it doesn't, those evaluations at the end are very useful. Please, let me know. All right, so we're not in the regression world right now. We're in a world that's deterministic, right? So we know exactly what's going to happen, right? So there are settings where things are very deterministic. So let's talk about, what is going to be, I had a better example for this earlier. So suppose, my walk is about 1 yard. Sorry for anybody who uses the metric system. So every step I take is about 1 yard. So about 3 feet, which is a little bit less than a meter. So if you ask me how far I've walked in 20 paces, it's about 60 feet. It is very useful for when I try to measure out bases in baseball, which is another very American reference. So we're going to walk about, in 20 steps, I walk about 60 feet. That's assuming that that's a deterministic function. So if I plug in 20 steps, then I've walked 60 feet after 20 steps, right? So this is something that we think of as deterministic. Now, if I went back a previous 5 steps, I'd be at 45 feet, right? Or if I go back 1 step, I'd be at 57 feet, right? And so what we're really interested in is we have this function of time. Let's suppose it's deterministic. And so that function is a known value. So for me, it's going to be, it's going to be 3 times t. F of t is equal to 3 times t in this example that I set here, right? That's a deterministic function. We know exactly how that's going to work out. All right. Now, we're often interested in differences. So we want to know, we know that I've walked 20 paces, that's 60 feet, right? But let's suppose I'm walking and you only observed me in the middle of that walk. You weren't paying attention. You're like, why is this man walking from one base to another? And so you can see how far I was at step 15, and where was I at step 14, right? At step 15, I was at 45 feet. And at step 14, I was at 42 feet. Therefore, the change in that step was 3 feet. And you can see, you can sort of figure out what this function is solely by using, that difference in time. Right? So even if we didn't know the function, we might be able to recover the function solely using that data. Right? All right. So what we're often interested in this class is changes over time. So what's the growth rate in GDP? What is the change in my LDLs? Or what is the change in the number of babies being born in a particular, square mile? Right? All right. Now, this is known as the first difference. We use the capital Greek letter delta to represent differences. Now, we could also be interested in the change in period t plus 1. That would be defined as yt plus 1 minus yt. Similarly, the change in yt plus 2 is yt plus 2 minus yt plus 1. Right? And so this just moves back and forth over time. There are some fields that require second differences. Very uncommon in economics, but I've seen it a handful of times. So there may be some scenarios where you need to take the difference of the difference, right? So you can think about things, like, what is it, like acceleration? You can sort of figure out these are more related to, say, like second differences or something like this. Oh, so there was a question. Sorry, somebody had asked about going back one step is 57 feet. So let me try to explain what I said again to make sure I said it right. All right, so let's suppose I walk 20 feet. If I walk 20 steps, then I've got to 60 feet. So f of 20 is going to be equal to 60 because it's 3 times 20. All right. So at f of 20, that looked terrible. At f of 20, I'm at 60 feet. At f of 19, which is one step back, I'm at 57 feet. So I went back one step. So we can think of this as f of t and f of t minus 1. So hopefully that clears it up. It doesn't just either write again or you guys can holler too. It's completely fine. All right, cool. All right, so there are some fields where we require a second difference. I don't know your field, so maybe it's relevant in your field. So let's talk about it. We can talk about higher order differences. And economics is really uncommon. So the way the difference operator was, so we use the power 2, which means do it twice. So the second difference is the change in the change of yt. So what you're going to do is first you do delta yt, which is yt minus 1. And then that difference operator is the change in yt minus the change in yt minus 1, which is the next line. So it's yt minus 1 minus yt minus 1 minus yt minus 2. Right? And so if we combine like terms, that's yt minus 2yt minus 1 plus yt minus 2. Some of you already see what's going on here. But for those of you that don't, so if we look at delta 0 of yt means no change. There's nothing happening here. So that's just, we're not making any difference. That's just equal to yt. Delta 1 yt is equal to yt minus 1. Delta 2 yt is what we have over here. Well, lo and behold, what do we get? 1, 1, minus 1, 1, minus 2, 1. That thing that was up in our 10th grade math classrooms, Pascal's triangle, is happening here. So if you needed to do any order difference, you could just pretty easily figure it out. So it's one of those scenarios, when are we going to learn this? Apparently it came up again. So you can uncover to the nth order if you want to, right? And there may be some areas of science where this is very important. I've seen this happen a handful of times in economics. I really haven't seen it outside of that. So how useful is this information? I don't know. I just think it's kind of cool to, when are we going to learn this, point those sort of things out. Okay. Linear first order difference equations. We're going to use these a lot. And this sort of model is used in time series all the time. But what we're doing here is we are not doing time series yet. We're going to look at linear first order difference equations where we know everything. Specifically, what we're going to know is we're going to know all the epsilons, we're going to know phi, and we're going to know some initial value of y, typically. Let's call it y naught. All right, so this is all going to be known. There's no stochastic element. We're not estimating anything. We just have this linear first order difference equation. We're going to learn how to work with this. And once we work with this, then we can use that to try to tell us something about a time series. Okay, so linear first order difference equation. Why is it called linear? Because y is a linear function of something. Why is it called first order? Because we have one lag of y. Yt minus 1. Why is it called a difference equation? Well, you could write this as yt minus 1, right? An equation because it's an equation, right? So linear first order difference equation is what we have. Now, in order to solve this particular difference equation, we're going to use something known as recursive substitution. We're going to just go back. So I'm arguing if I know all the epsilons, and I know phi1, and I know y naught, I can get any of the y's from here to infinity, right? If I know this information, I can get all the y's. So that's the basic idea. So I know phi1. In practice, of course, we don't. I know the initial value of y, let's call it y naught, and I know every single epsilon from negative infinity to positive infinity. Stupid assumption, but let's just suppose we know. So remember, our equation is yt is equal to phi1 yt minus 1 plus epsilon t. So when t is equal to 1, what do we get? We get that y1 is equal to phi1 y naught plus epsilon 1, right? y2 is equal to phi1 y1 plus epsilon 2. Go all the way down to, for any particular value t, yt is equal to phi1 times yt minus 1 plus epsilon 2, right? So that's fine. All right. I assumed I knew phi1, y naught, and all the epsilons. So if I know phi1, y naught, and epsilon 1, therefore I know y1, right? Okay. Well, if I know y1, then, and I know epsilon 2, then I can figure out y2, right? By just plugging y1 into here, then I get phi1 times y1 plus epsilon 2. In solving for that, I can write y2 in terms of things that I know. I know phi1, I know y naught, I know phi1, I know epsilon 1, I know epsilon 2. Then I could do y3, y4, all the way up to yt. And what this course really does is we're really interested in these patterns. Can we find these particular patterns? So phi, what we have is phi1 to the power 3, 3 here, 3 here. Phi1 to the power 2, 3 minus 1. 3 minus 1. Phi1 E2. So this is really 3 minus 2 in this power. And then we have epsilon 3. So we keep doing this till we get to time period t. And by the time we get to time period t, we get that we have phi1 to the power t, the initial value of y, phi1 to the power t minus 1, epsilon 2. This is how we can write this equation. So we can take it all the way back. So for any period t, we can figure out what the initial value of y was. And if we knew all the shocks, I knew exactly what yt was. If it's deterministic, we know exactly what happens. Now, In theory, if we don't know why not, we can keep going back and back and back all the way back to negative infinity. Now, we're going to make a very important distinction of whether or not phi1 is less than, equal to, or greater than 1 in absolute value. And that's going to matter a lot for these powers. All right. So suppose we have no data on why not. We can go back all the way back to infinity if we want to. So that's one particular setup here. All right, let me see. When we mean back, I guess we mean back in time. So when I say we're going back, forward will be forward in time, back will be backward in time. So think of last year is going back 1 year. 2024 will be going forward 1 year. We're going to be talking about going back in time and going forward in time. So do we do substitution backwards or we do it forwards? Right? And we're going to want to do both. We're going to want to use the past to try to predict the future. That's sort of the goal here.